You know that feeling when you watch a rocket launch and you can literally feel the ground shake? Well, that incredible power isn't just noise, it's controlled chaos. But what happens when that chaos is about to get, well, out of control? Today, we're going to dive deep into the violent vibrations inside a rocket engine. We're going to see how scientists solved a huge mystery where their predictions were off by a factor of, get this, 100. Okay, so our story starts right here, deep inside a powerful, solid rocket motor. You know, the kind that helps push absolute giants like the Ariane 5 rocket up into space. And let me tell you, this nozzle cavity, it's not a quiet place. It's basically a pressure cooker of swirling gases, insane heat, and just violent forces. Figuring out what's going on in there is absolutely critical if you want a safe launch. So the big problem, the thing that keeps engineers up at night, is something called thrust pulsation. The best way to think of it is like a deep, rhythmic, and incredibly powerful shake. I mean, if this vibration gets too strong, it can seriously damage the rocket, or worst case scenario, cause it to fail completely. So predicting how intense it's going to be, that's not just some academic exercise. It's absolutely essential for the mission to succeed. But there was a huge problem. The very first big scientific model they built to predict this shake, well, it was wrong. And I mean, not just a little bit wrong, it overestimated the vibration by a factor of 100. That's like predicting a nice, gentle breeze and getting hit by a Category 5 hurricane instead. This massive error was a huge scientific mystery. How could they be that far off? So, yeah, how could a really sophisticated model be so wrong? Well, that's exactly what we're going to find out. Let's think of this as a kind of scientific whodunit. We're going to follow the clues that one researcher uncovered to finally crack the case of the 100x overestimation. And here's our lead detective. Back in 2004, a scientist named Henry Y.W. Wong published this technical comment where he basically laid out the whole case. And he didn't just point out the problem. No, he actually identified the two key flawed assumptions in the original model that were causing this massive error. All right, clue number one. This one is all about direction. See, the original model made this really simplified assumption about how all those different forces inside the chaotic nozzle are interacting. It just assumed they were all perfectly lined up, for maximum impact. So this first flaw was this assumption of perfect alignment. The model treated two key forces, we're talking Coriolis acceleration and acoustic velocity, as if they were pushing in the exact same direction all the time. Think about it like this. Imagine two people pushing a car. If they both push perfectly straight ahead, right, they get maximum force. But in the real world of a rocket nozzle, it's more like one person is pushing straight and the other is pushing at a bit of an angle. Their combined effort is just weaker, because those forces are almost never perfectly aligned. So to fix this, to account for this imperfect alignment, Wong suggested using a much more realistic model. It's called a Gaussian distribution. And what it does is describe how the alignment of forces is strongest right in the middle of the gas flow, and then it gets weaker and weaker as you move toward the edges. This paints a much, much more accurate picture of what's really going on inside that engine. So what was the impact of just this one correction? Oh, it was huge. By accounting for this messy alignment, Wong calculated a weighting factor of 0.25. And just like that, this one single change slashed the predicted force down to just 25% of that original crazy overestimation. We're already a good way towards solving this thing. Okay, on to our second clue. Now, this one isn't about the direction of the forces anymore. It's about their timing. I mean, think about it. For two forces to have their biggest possible impact, they don't just have to push in the same direction. They have to push at the exact same time. And that brings us to the second flawed assumption, this idea of perfect synchronization. The original model just treated the whole interaction as if these two key forces peaked at the exact same moment, creating a perfect storm of energy. But as you've probably guessed by now, reality is a whole lot messier. This timing difference has a name. It's called a phase shift. And honestly, the best way to picture it is to think about pushing someone on a swing. If you push at the perfect moment, right at the top of the backswing, you add the most energy and they go higher. But what if your timing is off? If there's a time lag, you might actually slow the swing down. Your push is out of phase. Well, inside that rocket nozzle, the exact same principle is at play. The forces are just out of sync. So Wong did the math. He calculated that for this particular engine, which vibrates at a frequency of 850 hertz, the phase shift was really significant, somewhere between 80 and 90 degrees. Now, a 90-degree shift, that means the two forces are completely out of sync. Like, one is peaking just as the other one hits zero. They're basically working against each other, not together at all. And this time lag, you guessed it, it translates into another weighting factor. For a phase shift of 85 degrees, the factor is tiny, just 0.087. So what does that mean? It means the imperfect timing cuts the effective strength of that interaction down to less than 9% of its theoretical maximum. That's a huge reduction.
Okay, so we've got our two clues, an imperfect alignment and a critical time lag. Now it's time to put them together and see if we can finally solve the case of the 100x overestimation.
So here are the two steps Wang took. They're simple, but they are powerful. First, he corrected for that messy, imperfect alignment of the forces. Then, second, he corrected for their poor, out-of-sync timing. And with each step, he just chipped away at that massive overprediction. So what happens when you combine these two corrections? Well, you don't add the factors together, you multiply them. So you take 0.25 and multiply it by 0.087. That gives us a combined weighting factor of about 0.022. Let that sink in. This means the real interaction is only about 2% as strong as what that original simplified model predicted. Just 2%. And this chart, this is the aha moment right here. On the left, you've got the original prediction, just towering over everything else, 100 times higher than reality. But then look at the corrected prediction there in the middle. By applying just those two simple corrections, Wang brought that theoretical model crashing right back down to Earth, and it landed remarkably close to the actual real-world measurements. So, with just two really elegant corrections, the model went from being ridiculously wrong, a factor of 100, to being surprisingly accurate. Now it's only off by a factor of about 2. Just like that, the vast majority of this scientific mystery was solved. But you know how it is in science, right? When you solve one big puzzle, it often just reveals a bunch of smaller, more complicated ones. That factor of 2 difference, that's still something scientists want to figure out. The work is never really done. Wang himself actually pointed to some of the likely culprits for this small remaining gap. He said it could be due to even more complex physics, stuff like vortices merging together or changing their size and frequency. Or maybe there's still some subtle uncertainty in that phase shift we talked about. Each one of these possibilities is basically a brand new mystery, just waiting for its own detective to come along and solve it.
And that really leaves us with a final thought, doesn't it? This whole story, it wasn't about some revolutionary new law of physics. It was about something much more fundamental, carefully re-examining the basic assumptions we make. And it kind of makes you wonder, right? How many of science's greatest leaps forward are hidden, not in some brand new complicated theory, but in a simple, elegant correction that just brings our models one giant step closer to reality.